And happy birthday, dear Viktor Matveyevich. All the best wishes. So, we will talk about c₁-spherical bordism theory. And what is it? It's bordism theory based on the compact manifolds with some additional structure. And this structure consists of the stably complex structure on its complex structure on the stably tangent bundle. That is, we have a tangent bundle, plus trivial bundle, and we have a complex structure on this bundle. And the second part is the CP1 reduction of the determinant bundle. If we have a stably complex structure, we have a complex line bundle determinant, and we want, in the general case, this line bundle is reduced, it's induced from the map to CP infinity, and we want that this bundle induced from the map to the CP1. And it's a natural generalization of the notion of SU-bordism based on the manifold with CP0 reduction. It is a trivialization when we have, if determinant bundle is induced from the point, it's trivial, and it's equivalent to the reduction of the structure group to special linear or special unitary group. And we have natural forgetting maps from SU-bordism to c₁-spherical bordism and to all complex bordisms. And the stably complex manifold is c₁-spherical if and only if the direct sum of its determinant and the complex conjugate determinant is trivial. So in contrast to theory of SU-bordism and complex bordism, theory of c₁-spherical bordism, W, does not have a natural multiplication, because if we have two c₁-spherical manifolds, its Cartesian product is not c₁-spherical in general. For example, Cartesian product of CP1 and CP1 is not c₁-spherical. But if we have c₁-spherical manifold and SU manifold, then its direct product is also c₁-spherical. So we have MSU model structure on our theory W, and forgetting maps are in fact MSU linear. And we have the following theorem that the forgetting map is in fact an inclusion of a direct summand, and a projection could be defined by this following formula. Projection of the complex manifold M is the submanifold N in the direct product of CP1 and M dual to this line bundle, is the tensor product of tautological bundle and determinant. And it's a projection from the all complex bordism to c₁-spherical bordism, because this submanifold is c₁-spherical, because its determinant is reduced by the projection on the first factor. And its projection, we obtained that the c₁-spherical theory is a direct product of the theory of complex cobordism. And we can define then associative and commutative multiplication on W by the formula of this. We can have a direct. We can obtain. Take a direct product. It's not c₁-spherical, but then we can use our projection and obtain a multiplication on c₁-spherical bordisms. But okay, that's and we have that the ring of coefficients of c₁-spherical bordism with such multiplication is the polynomials without x2. In terms of the ordinary multiplication, we have that our multiplication have the following form. It's a direct product and this correction summand, where V is CP2 minus CP1 squared, and D is the operation which take a manifold M and get the submanifold dual to determinant. And for example, if N is already a SU manifold, then multiplication on N is just the direct product. For example, it's in the case when one of manifold is the image of this operation, because this dual manifold is of course SU manifold. It has a trivial determinant, and we have the ring, and we have such operation D. It is 0 if we consider D squared is differential, but what the relation between this D and the multiplication is not. We have not the standard Leibniz rule, but we have the following formula: that D of the product is the Leibniz part, and again some correction part. And what for me, it's very interesting what's kind of the structure of this differential, because it seems like some sort of deformation of the ordinary Leibniz rule, and I don't know what's it. And in fact, I would be very grateful if somebody tell me what is this. For example, it's equivalent that if we consider, if we consider identity minus CP1 and this operator F, then this properties and this Leibniz formula D of AB is equivalent that F is multiplicative, it's gamomorphism of the rings, and that F squared is identity, that is multiplicative involution. And but we have the extra property that it's such involution that F minus identity lie in some principal ideal generated by CP1, and I don't know what kind of theory we have here. I don't know. For example, I see such formula in one very surprisingly for me context, in the context of algebraic geometry in China this summer. I see that. Сколько времени у меня есть? Время 3 минуты сказать про этот контекст. Я думаю, да. What, for example, what if we consider the following thing? We consider such ring, Burnside ring of some field of characteristic 0. It's a free abelian group generated by all birational isomorphism classes of X is a irreducible variety, smooth variety, irreducible proper smooth variety over K. And omega is an form on X with logarithmic poles, at most logarithmic poles. And then we can, firstly, it's the direct sum of such groups is a ring, because we have take the direct product of two varieties, you decompose it on the irreducible components, and take wedge product of volume forms. It's a ring. And the second, we have such partial differential and for example, if X is smooth and the polar divisor of omega is a normal crossing, then the formula for D is the following. Let polar divisor have some components, irreducible components. Then for every set of these components, we have smooth intersection. And then using the iterated residue, we can define form, volume form on every such intersection. So we have some elements of our group, and we can define D on X omega by the sum with some signs of all subsets of A by such subclasses with some correction part where T is the class of P1 with the standard form. And turns out that if we define in such form, we have this property, and we have this formula. We have this formula x the y minus this class T, because it's P1. No, in fact, we have some correction part here, some sign, but it's not important. And it's the only and very surprising context where I have seen this formula, and I don't know what does it mean. I don't know what such formula. Okay, it's a work of this work ring with this formula. It's the work of Maxim Kontsevich, Georgy Chernykh, and some co-authors. Okay, but the stone projection is SU linear, and this multiplication based on it, it's SU bilinear, and of course any SU linear projection define such SU bilinear multiplication, and we have many projections, and so we have many SU bilinear multiplications. And for example, if we consider fourth bordism group, it's a free abelian group of the rank 1. It's generated by 8 CP2 minus 9 CP1 squared. Then we have the following result. For example, we can first we can classify all SU bilinear multiplications. In fact, we can classify all SU linear operations in complex cobordism, and most of them are vanish on the omega, and we can classify SU bilinear multiplications. It parameterized by one integer parameter s here, and then we can in fact we can classify all projections from complex bordism to c₁-spherical bordism, and we have such formulas again. And for example, and the coefficient ring for arbitrary multiplication is such form. When s is 0, is the multiplication defined by the stone projection, we obtain the previous formula. And we can classify all projections from complex bordism to c₁-spherical bordism. It's generated, yes. And we can, for example, classify all multiplication defined based on projections. They correspond to the case when C is even. And the final thing that such multiplication may be defined by projection which is commute with this operation. And it corresponds to the case when C divided by 4. And for example, we have the formula for all such projections. All such projections have this such form where we have P strong, this operation, some coefficients from c₁-spherical bordism, and delta is operations which take the bordism class and give the bordism class of submanifold dual to the direct sum of determinant bundle and the conjugate determinant bundle. And it's interesting because we have the following result of Botvinnik, Buchstaberg, Novikov, Yuzvinsky, that if we have such projection which commute with D, then multiplication defined on it, it's a multiplication on W. But if we have this commutator is 0, then this multiplication can be extended to a associative and commutative multiplication on mu by this formula. It's interesting observation from this paper. And it's exactly multiplication which correspond to projections which commute with D. Okay, and okay, the theory W doesn't have multiplication, one natural multiplication, but in some properties it's better than MSU. For example, it's complex orientable. In fact, any SU linear projection and any complex orientation of complex bordism define a complex orientation of W. And for any fixed projection and any complex orientation, we can obtain this orientation of W by from some orientation on complex bordism. And for example, W is in fact some kind of minimal complex extension of SU-bordism. More precisely, any any morphism to complex orientable theory from SU-bordism extends to morphism from c₁-spherical bordism. And what we can say in this case? Fix some multiplication, fix some complex orientation, and we can obtain some corresponding formal group law. And now, following it's on the first line, we don't see that, but it's right there that following Buchstaber's approach, we consider the following cohomology multiplicative cohomology extension of ordinary complex cobordism. And then we have multiplicative inclusion, and then we have canonical orientation, and the formal group law correspond to this orientation is the ordinary complex cobordism formal group law. But we have also the following natural transformation from W to gamma, and the main and very important observation of Viktor Matveyevich Buchstaber is that this transformation is multiplicative. And then we obtain other orientation, the image of our some orientation in W by this transformation, and we have corresponding image of formal group law. And if we express our orientation as a power series in our canonical orientation, then we obtain the standard formula comparison to formal group laws for two complex orientations on gamma. And then from this we can prove the following. We can for example calculate this formal group law modulo decomposable elements. And for example, for coefficients, we have the following. For coefficients of this group law, we have two strict equalities. And for modular decomposable, we have such equality. And yes, so here it's a formula. And what conclusion of this? What corollaries? So from this calculation, we can obtain the classical Viktor Matveyevich results. So we can this theorem, for example, for any SU bilinear multiplication and any complex orientation, coefficients do not generate the ring. And from this, for example, we obtain that there are no multiplication transformations from complex cobordism to W, which are surjective on the coefficients. And the second one, that if we invert 2 or the set of all Fermat primes larger than 3, it's 5, 17, 257, and 65,537, and maybe further. Then we can find complex orientation that the coefficients on the corresponding formal group law generate localized rings. And so the final part, that for any complex orientation, we have the corresponding multiplicative transformation. It's not, for example, projection multiplicative, because it's not surjective on coefficients from the previous result. But we have some multiplicative transformation. We have the corresponding genus, and we can consider, and we have the following result. The theory W with any complex orientation and any multiplication is remember exact. it means that we have the following isomorphism of cohomology theories of our c₁-spherical bordism and complex cobordism tensored on this ring, and no, we can obtain this. We can have this. We can consider this tensor via this ring homomorphism genus psi. So and I think it's all. Okay. Thank you very much.
Okay, let's invite the speaker. Are there questions?
Sorry, Georgy, there was a theorem which is by Viktor Matveyevich in 1972 and by you and Taras in 2023.
Yes.
What is the difference?
What's the difference?
Between
No, for example, Viktor Matveyevich thinks that's no difference in fact. In Viktor Matveyevich, he showed only ordinary multiplication defined by the Stone projection, for example. And no, maybe Viktor Matveyevich can, or Taras Evgenich can say something. I don't. Ну да, вот это вот. Ну да, вот это. Ну да. It was for the standard multiplication and.
it was for standard.
No, yes, of course. Because.
At that time, there was known just two projectors, a Stone projector and the.
Yeah, there are a lot of projectors and a lot of multiplications, but it did not consider.
Well,
yes.
Yeah, that not all of them coincide. Yeah, so. And yeah, Georgy,
At that time, there were actually two ways to define the multiplication on the ball, by a Stone projection and by the Corner-Freud projections, and it was known that they give the same multiplication theory of W, and there was a question that it wasn't quite clear that those projections are different, and Georgy first observed that they're actually different, although they define the same multiplication, but they vanish if you calculate them on higher terms, and then the question arose that whether this, and Viktor Matveyevich, of course, proved that for that particular Stone projection, which gives a particular multiplicative structure on the theory W, and it also gives some canonical orientation coming from that projection. So there are lots of multiplication and lots of orientation on W, but then once we realized that there are many projections, and including those two classical ones are different, then the question arose whether this result still holds for arbitrary multiplications and projections, and maybe Viktor Matveyevich cannot know.
Thank you very much. I am happy that there are young, brilliant scientists who like work in this area. In this, yeah, I should like give a few comments. First comments. You mentioned the paper for authors. Ботвинник, Буштабер, Юзвинский и Sergei Petrovich Novikov. Story such. In that time, Sergei Petrovich spent some time in Maryland. And he's thinking about the quantum bordism theory. And suggests to Botvinnik and Yuzvinsky, and you know, Yuzvinsky is one of the well-known experts in the combinatorics, on the singularity theory, and they start to find a new multiplication, because if you have complex cobordism, multiplication, very simple. You consider two manifolds, you consider direct product, nothing else. You can consider the sum, which the union, division union, nothing else. And they start to work. And when they start to obtain some result, Botvinnik mentioned, why we repeat the result of Viktor Matveyevich 1972. For Novikov, it was surprise. And after that, he immediately asked me to start work together. And when I go to the Maryland, we work together. But our result in this area published in Russian surveys. In the central topics, which is still problem now. It will be very interesting if young scientists who are interested in cobordism consider this problem. What is the problem? In complex cobordism, we have some disjoint union, have product. Question: can we deform product such that it will be still associative up to some? It is look what how Drinfeld introduced quantum group. The same. He asked, can we deform multiplication which respect diagonal? Here the question, can we deform multiplication such that it will again associative about disjoint union? More was very interesting to find. If you in cobordism you have commutative product, because manifold you can change multiplication, which is non-commutative. Certainly, what in our paper we give example, you know, non-commutative multiplication, but the general problem still open. And very interesting. Can we construct universal multiplication in complex which respect disjoint union of false? Of course, it is certainly it is a very interesting problem, but certainly needed some idea, some approach, some construction. And certainly, I am happy that successfully in complex cobordism, there are one small problem. There are a lot of problems. One of the problems such. Why? We must consider only closed many. Maybe we can use a boundary. So this strong my people, Oleg Mironov, who unfortunately died now, but he would follow what is exactly what is my paper, considers a case. We consider manifold with additional condition on the boundary. You go to the boundary and obtain direct product. Manifold one. It turns out it gives you possibility construct theory cohomology, and the first it was a geometrical, but it's geometrical because we have additional theta as cycle in cobordism, not structure on the boundary. There are very deep, very exciting problem. Consider more. For example, we can consider such a manifold which boundary no. If you look and obtain manifold with smooth boundary. But from point of view of cobordism, it is not good. The kernel is additional structure. Open problem, construct theory of cobordism, where cycle it is a manifold Thanks again, Georgy. And certainly I should like fix it that in bordism theory, which starts from Poincaré, 1985, and the fantastic result, Pontryagin, Tom, Milner, Novikov, and so, till now, there are a lot very fundamental, exciting problem, which it's our happiness relate us with quantum mechanics, quantum physics, combinatorics, and
Okay. Now we have a coffee break and continue in 4:30.